Welcome to the 2024 Ruth and Irving Adler Expository Lecture. And these lectures were founded by Professor Steve Adler from our School of Natural Sciences in honor of his parents. Irving Adler was a well-known, did a PhD in math and wrote many books about mathematics. And the goal of this lecture series is to offer a kind of glimpse of math in a way that can be appreciated by a non-specialist. And our speaker today is Tadashi Tokieda. I first saw Tadashi, I think, at a lecture he gave at Courant, the Christmas lecture around 2007, 2006. And I still remember this lecture after all this time. There was a full auditorium that were completely transfixed. While this man at the front was playing with toys. And for a full hour, we watched him play with toys, and out of these little toys, he summoned the most intricate and interesting scientific phenomena. Okay, so Tadashi is a professor at Stanford, and a selection of highlights of his career before that is that he was a painter, he studied philology, and he was a plumber at various times of his life. So I'm very pleased Tadashi is able to join us today, and please join me in welcoming him to this lecture.
This lecture is established by Professor Stephen Adler and honors the memory of Irving and Ruth Adler, his parents, and of some of the wonders that they wrought for the world. You know, traditionally, mathematics is expected to generate unexpected applications in physics. As an admirer and follower of Adler's course, a mischievous idea occurred to me of applying physics to mathematics, the other way around. That way, I thought that we shall see that the parents inherit some surprising insights from their son. At the end of a lecture like this, there is often an awkward pause because people feel polite enough to ask questions, but they don't know what to ask. In such an awkward moment, let's see a good photograph to ask a question about what is this apple tree doing? And we shall see that if you ask a question. Let's begin with the most famous of mathematical theorems, and that's Pythagoras. It was back a long time. And as usual, we have a right triangle PQR with the right angle at R. And our business is establish the usual identity lengths of that triangle. Now, taking this triangle as a base, let's make a box, an enclosed box of triangular base and height h enclosed on all 5 sides, which I attach to a vertical axis around which it can pivot, spin with no friction. Now comes an interesting step in this argument. I fill this box with pressured gas at pressure P. This gas is going to push against all the sides of the box, but the up and low pressures, balance each other. And anyway, the box kind of move in that direction. So we shall look at only the lateral forces. So this is a bird's eye view from the top. P stands for pivot, R is right angle R, and Q is a misspelling for corner. Now, you see that the entire pressure distribution on the side PQ, when I say side PQ, of course, there is a thickness or the height H, which is sticking out from the picture, and can be replaced by a single representative force FPQ acting at the center of that face, and similarly for FRP and FAQR. Well, you see immediately that this FPQ, the purple force, has a tendency to spin the box in the counterclockwise manner, whereas the other two forces, FRP and FQR, conspire to try to spin it clockwise. But we know, because we lived in this universe for long, that just by filling a box with gas will not set it in motion. Otherwise, you would have a perpetual motion engine or that kind of thing. So the torques, that is, the tendencies to spin, must balance. Yes. So the torque due to FPQ must balance the torques, some of the torques due to FRP and FQR. We shall start filling the formula. And for the first two, it's very easy. The torque due to FPQ is the distance from the pivot to the line of force, which is half of PQ, and then times FPQ. That's the tendency with which you spin it counterclockwise. And similarly, for FRP, the distance from the pivot to the line of force is half of RP. so far, I did not use at all the hypothesis that this is a right angle triangle. It is here, and only here, that I shall invoke that hypothesis. I claim that because this is a right angle, the torque due to FQR, that is the distance from the pivot to that line of force, is exactly half QR. You see, that distance. If this was an acute angle, so it's less than 90 degrees, the line of force will pass nearer P, and if you were obtuse a little more than 90 degrees, it will pass further, but because it's 90 degrees, that distance is the same as distance, and that's half QR. It's only here that they use the right angle hypothesis. But now we're almost home, because what is force? Force is pressure times area. Well, what is pressure is P, small p, and area is, remember, there's height sticking out, it's H times PQ, so I just replace that here. And so you see that small p times H divided by half appears in all the terms. If I clear that, you get at the end, PQ squared equals RP squared. Mazal tov. And of course, if you follow through the same motion with an arbitrary triangle, you end up with something called cosine law. That's a fourth extent that you can do. So that was the most famous of the identities. Now, let's do some of the inequalities. Okay. Probably the most famous and the most useful one is Cauchy-Schwarz inequality in the Eastern Bloc. It is Cauchy-Schwarz-Moniavsky inequality. And to deduce that, let's imagine a lot of slats, wooden slats, if you like, which are sliding in frictional contact. Let's say the first slat has mass m1, moving with speed v1. They're all moving in the same direction. And the second one, m2, moving with v2, and so on and so on. Okay, so this is the initial condition in which I prepare the system. I just sit back and watch. I always sit back and watch. That's how we do things. After a while, you know what happens. There's mutual rubbing. So they eventually end up moving at the same speed. Yeah? Well, asymptotal to the same speed. And we know that speed, what speed is, because those mutual rubbings are internal. There's no momentum that is put in or no momentum that is taken out. So the momentum must be conserved, which means that this average speed, which I shall denote by the triangular bracket V, is the total momentum, sum of mv, divided by the total mass, m. That's what it is. Whereas the momentum is conserved, the energy is dissipated. We lose energy because rubbing loses a lot of energy into heat. So let's write down how much the energy is lost. So before energy, after energy. Before, it's very easy, it's the kinetic energy, half mv squared, summed over. But after waiting for a long time, it is half of where the entire thing is moving as if made of one body, so the total mass, times the average speed squared. But we know what the average speed is. You just plug that in, clear the denominator, and what you get is something like this. The sum of m times sum of mv squared is greater than or equal to the total square of sum of mv. And that looks almost like Cauchy-Schwarz, but it isn't quite. So let's convert that in Cauchy-Schwarz by changing variables. There's actually rhyme or reason to this change of variables. What we shall do is replace each m by m squared and replace each v by v over the corresponding n. And then the result of that transformation is that you get the sum of not m but m squared. And here you get m squared, but the v is replaced by v over m, so if m squared cancel, you get the sum of v squared. The right-hand side, mv, is invariant under this transformation. That's also quite interesting, but we shall pass. And that's it. And that is exactly Cauchy-Schwarz. Okay. However, you are right to start complaining. Thank you very much for complaining. In this case, there is something wrong. For example, all the m's in this argument must be positive because they are masses. But in Cauchy-Schwarz, we know the m's can be positive or negative. So how do you deal with that? That's okay, because you see, here, when you change m to m minus m, it doesn't see the difference. It doesn't see the difference. But here, of course, that's where it's affected. You see, changing a certain m is tantamount to changing the corresponding v by its sign. So instead of going right, you can go left, and that's all it is. So then if you do that, write that argument, then you can take care of negative n. Much better sort of complaint is, well, mathematicians and physicists are very greedy people. You want to milk everything out of an argument. So what about the sharp case? It is called Cauchy-Schwarz inequality because generically it's inequality, but sometimes it becomes an equality, exact equality. When does that happen? Well, you want to do mathematics, just go back to physics. Well, it means that there was no loss of energy. when can there be no loss of energy? When there's no rubbing, that means that all the velocities were the same to begin with. But that's in the order coordinates, you see. In the new coordinates, it's V1 over M1 equals V2 over M2 and so on. But that expresses exactly that the vectors V and M are proportional to each other. And that's the sharp case of Cauchy-Schwarz. And you can do a completely different argument in order to get Helder. And that's more recent. And because the powers are very strange and you don't have the energy interpretation, you have to do something. But okay. Another useful inequality, perhaps the second most useful, is what is called arithmetic mean geometric mean inequality. You see, when we think about the average, of course, we think of adding A and B divided by 2. But if the problem is multiplicative, then it's much more natural to use the multiplicative version of average. That's called the geometric average. So you take A times B and take the square root, correspondingly for n variables. So AMGM inequality, as it's often abbreviated, says that arithmetic mean is always greater than or equal to the geometric mean for all numbers. Okay, so let's deduce that from physics. Here we have blocks of material with masses M1, M2, M3, and so on. They are in contact. And let's say they are made of the same material, or if you like, have the same specific heat, C. What is specific heat? Let's recall that concept. So heat is a form of energy. And so if you want to raise the temperature of an object by 1 degree, how much energy do you have to put in? How much heat do you have to put in? Per unit mass. That is called specific heat. Okay? And so it's measured in, the joule, that is the measure of energy, divided by kilogram, divided by degree, Kelvin, if you like. Okay? So if you like, it's the thermal equivalent of inertia. So, some material like water doesn't want to change its temperature very easily. So it demands a lot of heat before you raise the temperature. And, you have to cool a long time before it lowers the temperature. And some other material like metal has a very small inertia. So water has a large specific heat C and metal has a small specific heat C. Okay? So let's start from that setup. In order to clear the argument a little bit, I shall allow myself to introduce notation. So Pi is a proportion of the mass that this I's mass occupies among the total mass. Okay, so Pi, so capital M is the total mass. So in this notation, P's are all between 0 and 1, and they add up to 1. So if you think of them as probabilities or weights and so on, that's fine. Okay. So let's say that these masses have temperatures T1, T2, T3, and so on. And now you place the bodies in thermal contact. And do you know what we do? We sit back and watch. And because you lived in this universe for long enough, again, that eventually they settle to a common temperature, asymptote common temperature, which I shall naturally denote by triangular bracket of T. And that's the average with respect to those weights of T's. Well, it's very easy to see because if you have a huge mass and small mass, and the final temperature will be more influenced by the huge mass and a tiny bit influenced by the tiny mass. The proportions are like this. Okay. At the same time, let's say that in the course of this process, the ith body, one of the bodies that you're focusing on, change this temperature by a small bit increment dTi, or decrement for the matter. So how much heat did it receive when it changed the temperature by this much? Well, according to the definition, the very definition of specific heat, it's equal to the specific heat T times the mass, which is capital M times Pi. Yeah, that's a proxy for Mi, times the temperature change Di, Et. Okay, that's the heat it received, that ith object received. Then its entropy changes by that heat it received divided by the absolute temperature. Okay. If you are uncomfortable with entropy, there's no reason to be. Entropy is as useful as energy in solving problems, but this can be taken as a thermodynamic definition of entropy. There are 3 approaches to entropy: thermodynamic and statistical physics and information theory. They're all related, but have different nuances. Here, the SI, so that's the entropy change for the ith body, is simply this divided by that. But if you learned a little calculus, you see dt over t. That's the logarithmic derivative. It's the derivative of log t, and that becomes dt over t. So you write it like that. I copied it in the top line. So that's for the ith body, but now let's run the process from start to finish. So you just integrate, as we say, both sides. So the entropy of the ith body at the finish minus the entropy which had at the start is equal to the integral of this. So Cm, that's of course constant, and Pi times the final value of inside the log is of course the final temperature, which is the average, minus Ti log, this is the initial temperature. Here I commit the crime of Les notation, which is that I use the same notation Ti for the initial temperature and the variable. Please forgive me, it's the last time that this confusion is going to happen. Okay, so this is what it is. That's the entropy change between start and finish for the ith body. Let's now sum over all the bodies. What's the total entropy change for the entire system? Well, I just sum over I, that's a summation. And again, the Cm is a constant, but then Pi's add up to 1. So it becomes invisible as 1. But here, instead of adding right away, you put P inside the log, so it goes on the shoulder. And of course, the sum of log is log of the product. That's why God created logarithm. And so log of the product of Ti, Pi is what it is. So far, everything was pure manipulation. However, now we shall invoke the most important thing that we shall mention this afternoon. That's the second law of thermodynamics, which says that in a spontaneous process, the total entropy should increase. And if you want it to decrease, then you have to do something really clever from the outside. So that means that this sum is positive. But look, sum is positive means that the log, the increasing function, the inside of log, this must be greater than that. And if you unpack it, you get Pi times Ti plus T2 plus T2. Arithmetic mean of P is greater than or equal to Pi to Pi times T2 to T2, the geometric mean of T's. That's the AMG mean, right? What about the sharp case? The sharp case is sharp case means that the entropy didn't increase. How can that be? Because there was no heat exchange. That means surely that the temperatures were equal to begin with, and that's of course the sharp case of AMG. I mentioned that there were multiple approaches to entropy, and one of them was the information theory that goes back to Shannon and beyond. So allow me to make a digression. In fact, this entire lecture is a digression of sorts. By proving the infinitude of primes, that is, there are infinite many primes. We know that, don't we? Although I have never seen infinite many primes. And the only thing that I ask you to believe from information theory is really nothing complicated. So if you want to code some large number, n, let's say, you have to pay an information cost in order to code. You can't do it for free, and the cost is log n bits. The base doesn't matter because they're all proportional, but traditional log base 2, if you like, log n 2 bits. That's how much information cost you have to pay in order to code n. Of course, because if only to write down n in base 2, you need so many symbols. Of course you do. So that's the only thing that we shall have to use. Now, let's imagine, remember I'm trying to prove that there are infinite many primes. Imagine that you want to code some number n. But let's take a detour by first prime factorization. I'm taking the prime factorization of n. So it's the product of p to e. Yeah, so the product of various primes to various exponents, e is exponents. And so by the uniqueness of prime factorization, coding n is exactly equivalent, information theoretically, to coding all the exponents. There seem to be infinitely exponents, but finitely many of them will be zero. So that's okay. Yeah? Okay. Now, how large is each e? It's actually not too difficult to get that to estimate because you see, if you in this product take only one of the factors, then n is greater than that factor, but the smallest prime, if I remember, is 2. So it's greater than or equal to 2 to ei, and by taking the log on both sides, there's 2 if you like, each exponent ei is at most log n. Okay, so each exponent has size log n at most. That's how large it is. Now, remember that boxed formula, yeah, boxed recipe. So by that boxed recipe, because each e has at most size log n, each exponent costs at most log n bits to code. Okay, because that's the maximum size. So log of e is the cost, so log of n is the maximum cost. Okay, so each exponent costs that much. So far, again, everything was fine, no mistake. But now we go for the contradiction. Suppose, for a contradiction, that there are only finite many primes in this universe. Let's say a ginormous number, but finite number, k. Then how many primes are there? K primes. How many exponents are there? There are k exponents. So an n, generic n, will cost at most k times log n bits to code.
But actually, that's far too small because I know that true order, it's right here, it's log n. And if you learn anything in calculus, it is that exponential grows much faster than any polynomial, so log n grows much faster than log n. In other words, if you had only finite many primes, you'd be in the presence of a coding algorithm, which is too good to be true. That's the argument. Okay. And of course, you can quantify this argument and then get some very, very weak estimate for the size of the nth prime and so forth. That's
Weaker than Euclid.
yeah, weaker than Euclid. Okay, good. Now, that was, if you like, a diversion of this physical approach applications of mathematics, but to that discrete world. So I'm going to give another discrete example in a more playful manner. Here is a game that I would like to play with you. It's called multiplicative scoring, or I call it multiplicative scoring. Let's say that you have a number, an integer, k, which I split into two parts, I and k minus I, so that they add up to k, okay? And we say that each time you split it like this, you gain a score for yourself of I times k minus I, okay? The product of two terms into which you split it. An example, let's start with 6. I can choose to split into 2 and 4, 2 splits into 1 and 1, 4 splits into 1 and 3, 3 I can split into 1 and 2, 2 splits 1 and 1, everything became 1 and I stop. How much score did I collect? In the first step, when I split into 2 and 4, that's 2 times 4, that's 8. In the second step, 1 times 1 here, 1 times 3 here, so I scored 4. So if I add all of them, I scored 15. That's my score. But of course, this score depends very much on how I split. You know, I could have split 6, begin by splitting 6 into 3 and 3, and so on. There are many trees, as we say, in graph theory. By the way, let me complain about something. You know, the computer scientists seem to believe that a tree has a root at the top and then grows towards the bottom, and the leaves are all at the bottom. I usually see trees that have a root at the bottom and grows upward and so forth, but let it be. So this is a tree, and so it depends on the tree. So question, which splitting algorithm, which tree that you choose maximizes, or if you like, minimizes the total score? Now, those of us who are over-educated, I know that this room is full of over-education, might have started thinking, well, maybe it has to do with AMGN. Arithmetic mean geometry, because we are trying to maximize the product while keeping some constant. And of course, I have just talked about the MG, and this is called psychological approach to problem solving. But now, think of it this way. We had this terrible time of COVID and so on, during which apparently the delivery business really thrived. So let's say that you, at the Institute for Advanced Study, you received lots and lots of boxes of the exactly identical size, or the exactly identical shape and the and weight. And for some reason, it possesses me to stack them into a single power. This is very, very heavy work, so I have to ask my friend and teacher, Professor Sana, to help me. And then we just have to lift it, and we're using knees, not back, and so forth. And so you have a tower of height I, and there's already a tower of height k minus I, and I want to put it on top and to make a tower k. So this is really hard work. And how much energy do we have to expend in order to achieve this? Well, think of it this way, otherwise it becomes complicated. So this has some weight I, and I have to slide it upward by what distance? By this distance, k minus I, and then I can slip it sideways, and that doesn't require any additional energy. So it's I times k minus I. That's the potential energy for this stacking. That is I times k minus I. Wait, that's the same thing as my score. In other words, this stacking task is the inverse to our problem. So now we can go down. Let's say that we have a delivery of n packages all on the floor on level 0. And I end up piling them into a single tower. And please remember, this is the European way of counting the floors. The ground level is 0. And then 1, 2, all the way to n minus 1, because there are n passes. By the way, I used to be in classical philology at the University of Tokyo, and then an old but very, very distinguished philologist who was a colleague of mine had his the office moved from the 2nd floor to the 3rd floor. In Japan, we count the floors the American way. And he bitterly complained that whereas the floor number increased only by 50%, number of steps that he had to climb doubled. Another thing that while I'm having a digression, I used to meet lots of ancient historians, and I asked all of them, how many years elapsed between 20 BC and 20 AD? And it's amazing that almost none of them gets it. They all say 40 years. Of course, no year 0. Between one BC and 180, there's only one thing here. It's a bit worrisome for history. But anyway, so if you stack them all up, what is this? Well, at the end, you see, of course, the total energy, which is the sum of all those heights. And if I know anything, I know the sum of 0 plus 1 plus 2 plus all the way to n minus 1, which is n minus 1 times n over 2, independent of the splitting algorithm or the tree. So in this case, n was 6, 6 minus 1, that's 5, times 6 divided by 2, that's 15. That's what 15 was. So the question was totally moot. It doesn't matter what you do, provided you don't do anything suitable, like going back. It's always going to be that constant energy because of the potential argument. And this would have been rather tricky to discover if you weren't thinking physically. Now, let's go to a topic which is between discrete and the and continuous. Who has in this room heard of Pick's formula for the, many of you have, very, very overeducated indeed. So, nowadays, in this age of pixels, this is a very natural question indeed. So here is what is called a lattice polygon. You imagine on the plane, only points whose coordinates are integer points. Okay, those are called lattice points, those cross points. And lattice polygon is a polygon whose corners are all integer points. It doesn't matter that the edges go through some strange zones, but the corners or the vertices must be lattice points, okay? Now, that's a lattice polygon, and the question is, what's the area of such a polygon? Well, again, in this age of pixels, it's very easy to guess that, well, you count the number of pixels inside, so number of interior lattice points, that's the first term, and there are 5 of them, so that's going to be a good approximation to the area. But there's actually something better that we can do. You know those boundary lattice points that appear on the plane? Well, boundary points are kind of half inside and half outside, aren't they? So they should contribute 1/2. So you get half the number of boundary lattice points, and then you subtract that incomprehensible and mysterious -1. Where does that -1 come from? That -1 makes this formula exact. It's not an approximation. So for any lattice polygon, this is the exact formula. For example, for this picture, there are 5 interior lattice points. And if you count, there are 11 boundary lattice points. And if you do the arithmetic, it's 9.5. That is the area of this lattice polygon. Assume this each square is 1. Amazing. So how do you prove this? The usual proof of Pick's formula usually sort of divides this into fundamental triangles. And you say that, well, it doesn't have any interior point. That should have an area 1/2 and so forth. But we shall do physics. And the physics will reveal where the main difficulty is, as far as we are concerned, of generalizing this to higher dimensions is. Okay. But the digression before. Please believe Pick's formula for the point, for the time being. In any geometry, people really like to talk about regular objects. Regular triangles, regular quadrilaterals. These are called equilateral triangles and squares, and then regular n-gons and so on. So how about regular polygons in lattice geometry like this? Are there polygons whose corners are lattice points and which are regular? Okay, so I'd like to show, as a digression, that regular n-gons don't exist in this geometry, except when it's a square. Well, of course, lattice squares exist. You have this square. You can also tilt it a little bit. Yeah, you can see that. But except first, there are no other regular polygons in lattice geometry, and here's a proof. Let's treat the case when n equals 3 and n greater than or equal to 5 separately. N equals 3. If there were an equilateral lattice triangle, I claim that the area would involve a number like square root of 3, because you see, if you take the bottom base and the height is square root of 3 times, divided by 2 times the bottom or something like that. And so you get square root of 3 somewhere up here. But Pick's formula says there can be no square root of 3, because you see, at worst, what you're going to get is counting integers and divided by 2. Half integers is the worst you can get. So there cannot be possibly anything irrational like square root of 3. So Pick prohibits such a thing. You cannot have equilateral triangle that is lattice. Okay? So that's the first case. But the second case, 5 or greater, that's even better. So suppose that there are, say, lattice regular 5 ones. Take the smallest of them. You can't have arbitrary small ones because we're doing lattice geometry. Yeah? You are stuck at the bottom. So here's one. A lemma. In lattice geometry, if you have a parallelogram, which is a lattice parallelogram, and if 3 corners of parallelogram are lattice points, then the 4th corner is also a lattice point. Do you believe this? I can just translate, okay. So, in particular, in this picture, because those are lattice points, looking at those 3 points, this is a lattice point, all right? And looking at those 3, this is a lattice point, and then presto, you get this. In other words, you have produced a descent, and you cannot produce an infinite descent because you are stuck at the bottom. That proves a contradiction. Okay, so let's go back to P. That's the formula that we would like to prove. And what we shall do is, I'm very, very honored by a vast sort of crowd of people who came to listen to my CD lecture, but very serious in my purpose of honoring Professor Adler's parents. So, taking advantage of this vast, infinite audience, I shall do the following operation. So, on the lattice point, please imagine an infinite plane, Euclidean plane, with lattice points. So, extending to infinity, you see in all directions. And at each lattice point, you put an upside-down glass containing 1 unit volume of water. That's what it is. And each of you, the infinite of you, stands in front of each of those glasses. Okay? And at my signal, all of you lift the glass at the same time and thus float the plane. Okay, there are waves all over the place, but eventually the water will come and settle to a flat surface. How deep is the water? Of course, depth 1. Yeah, because there was 1 point per each unit area, and there was 1 unit volume of water. And so, somewhere in this lake that was uniform, you see the picture of lambda, this lattice polygon. And water above, the volume of water that is sitting above lambda is precisely equal to the area of lambda because depth is 1. Is that okay? I haven't lost anybody? Good. So, where did this water come from? Another lemma. Mathematicians like lemmas. So, if you look at this picture of lattice geometry and water flowing and so on, look at the midpoint of every edge of lambda. So, edge of lambda can be a lattice point, or it doesn't have to be a lattice point. But look at a midpoint. Around this midpoint, you see the picture of the lattice. Forget about the lattice polygon for the time being, but the lattice points as a whole is symmetric, right? By 180-degree rotation. Because, everything that's there is something here. Okay, around every point. So that means that the water pattern, the flooding pattern, must be symmetric around the midpoint of every edge. Which means that if you imagine an edge, and there's water flux going this way, there must be of necessity a water flux going the opposite way because it's symmetric. Yeah. So without loss of generality, usually abbreviated WLOG, sometimes it stands for without loss of generality, you can assume that each edge, in fact, the entire boundary of the polygon is impermeable. That is, no water goes out, no water comes in. You have a solid wall. That simplifies the rest of the argument because now I can ask, where did the volume of water above this lattice polygon lambda come from? Well, each interior point contributes 1 because you release the 1 volume of water and it can't exit, so it has to stay inside the lambda. Okay? What about the point on edge? For example, a point like this, on the edge, well, half of the water goes in and half of the water goes out. If you like, there's pi radian out of 2 pi that went in, so 1/2. So green corresponds to that interior contribution, and blue corresponds to that boundary contribution. Okay? What about a corner like this? A corner that makes an angle theta. Well, the same thing. So theta worth of water comes in out of 2 pi worth. But you know that if you have, so that's theta of 2 pi, but you know that if you have an n-gon, it doesn't have to be like an n-gon, the sum of the interior angles like this, sum of theta, is n minus 2 times pi in Euclidean geometry. You can divide that into n minus 2 triangles if you like. So by dividing this identity by 2 pi both sides, the sum of those contributions comes out to be, well, divided by 2 pi, so you get n over 2 here, and 2 pi divided by 2 pi, that's minus 1. So that contributes, again, to the boundary, but there is this mysterious red thing, and that was the combinatorial jump that we had to subtract, minus 1. And that's Higgs formula for you. Okay, and you see how this will be difficult if you want to generalize this to the volume of, say, a lattice polyhedra. You see, there are generalizations, they were studied by MacDonald and Eckhart and so on, these polynomial approaches. But the problem is everything is fine. In fact, the physics argument goes through, but at the end, there is no such formula. Easy formula, combinatorial formula that gives you the total sort of solid angles of all the vertices and so forth. That's where you get stuck. So if you can overcome that, you can write down this explicitly for all dimensions. Okay. And now, since we are kind of straying into algebraic matters, we shall do the roots of the algebraic equation. And this is a very classical subject. So you have some, many people think that mathematics is all about equations. I get really annoyed by this, there are equations, but there are other things in mathematics. But you have an algebraic equation. Let's say that you have real coefficients. And when you see something like that, let's split it on both sides so that all the coefficients on either side is positive, okay? So that's what we prepare. We want to find the root of such a thing, that is x such that this is satisfied. So here is how you do it with physics. Let's stick various objects like this and ask, what kind of Archimedean buoyancy do you get upward? Well, Archimedes discovered if you put something inside water, there is a lift or the buoyancy, upward force, which is equal to the weight of the water that has been displaced. Yeah. So if you, for example, sticking something like this cylindrical, it's all closed, okay, enclosed. To depth x, the amount of buoyancy that you get will be proportional to x because the cross-section has constant area, okay? The deeper you push, the more proportionally more buoyancy you get. If you stick in something paraboloidal, it's very easy to compute that to depth x, you get x squared buoyancy. And similarly, if you get something pointy, x cubed buoyancy, and you have to have something non-convex, and then x cubed, and so on. So, what about the constant buoyancy? Well, you stick in something that is maybe like this. As soon as you go in, you get some constant buoyancy, but if you go out, there's zero. So you can have constant too. So how do you find a root to this kind of equation? What you do is you make this kind of gadget. And so you have a long rod, and at various distances from this pivot, you hang those objects, okay? And you attach those objects. Let's say this is the coefficient of x, this is the coefficient of x2, and this is the coefficient of x3, and this is the coefficient of x, and so the x0 and so forth. And then it can pivot around here. And then you sink the whole thing into water. Yeah, and sometimes this side will have more buoyancy. That's something, but at some point they will balance and leave you the pleasure. And then where it balances, that depth is the and it's an interesting exercise to do this for complex numbers. Okay. Let's kind of try to begin to conclude this talk by doing something that is slightly less classical. And really the key quantity in topology is something called Euler characteristic. And they are the best of reasons. You know that by the splitting principle, if you understand the Euler class, you understand all the other classes and so forth. But anyway, Euler characteristic. And Euler characteristic in this case will be thought of combinatorially. So you just draw some network and count the number of vertices, number of edges, number of faces, and you do the alternates and so forth. And I want physics to compute it for me. Okay. So here is one. Let's start with the simplest of all these sort of surfaces. Let's say S2. This is a two-dimensional spherical shell. So non-mathematicians always get confused between spheres and balls. So sphere for a mathematician is a spherical shell. It's called like an eggshell. And ball is all the solid inside included. Okay, so this is a spherical shell. S2, 2 is dimension. And some people like to say it's genus zero surface. And let's say you cover it with some electric circuit made of wire, except a copper wire, having beta 0 nodes, beta 1 wires, and beta 2 panels. Panel is a fascist name for these faces, if you like. Okay, so here is one coverage. And it doesn't matter which cover you take that cover. Now comes the interesting argument. So you lead 2 wires from any two vertices, and I want to connect it to a voltage. And this, again, is a very dangerous operation. So I'm going to ask my friend Akshay to do this for me. It's a very, very high voltage battery, and he very gingerly goes and then wants to connect those two things. And you know what happens as soon as he connects? Zap! And the currents flow through all the wires at the same time, or almost at the same time. Okay? How much current flowed through each of the wires? I don't know because this problem is too difficult, but nature found out the values instantly as soon as actually touched the battery. So the philosophical point is that the problem must have been solvable for nature. I'm not intelligent enough, but nature is intelligent enough. So there must have been enough information. So what are the values of current in the wires? How many unknowns and how many constants were there? Let's enumerate them. How many unknowns? Well, the number of wires, of course, beta 1. That's fine. How many constraints? These constraints come from what is called Kirchhoff's laws in circuit theory. And the first of Kirchhoff is that if you look at each node and the number of wires that meet in there, well, the amount of current that goes in must equal the amount of current that goes out. Otherwise, there will be an accumulation, depletion of charge, and that's not good. Okay? If you like, it's a divergence zero condition. And there seem to be as many as beta 0 conditions. We shall come back to that. It's actually not true. Second Kirchhoff law says that if you see a circuit around this little panel, then around each panel, you can have a clockwise current, but it must be equal to anti-clockwise current. Otherwise, there will be some kind of circulation, which is not good either because it's a potential station, harmonic station, and so forth. If you like, it's a curl 0 condition. So there seem to be as many as panels of conditions that beta 0, beta 2. But those counts are actually overcounting a little bit because the actual number of independent conditions are beta 0 minus 1, beta 2 minus 1. Let me convince you of this. Take this network and impose the divergence 0 condition at all the vertices, all the nodes, except the top one. Okay? So at each of the nodes, as much current is going as going out, coming out. Okay? Except the top one, I don't know anything about it. But I claim then at the top one, automatically as much current comes in as goes out. Obviously, because the net current that went into the top is the net current that sum total of all the other nodes have ejected, and net current that went out is, of course, the sum total that all the other nodes have absorbed. So that condition is not independent of the others, and that's overcome. It has to do with the fact that if you remove the disk, then the rest becomes contractible. But anyway, so it's beta 0 minus 1, beta 2 minus 1, that's overcounting. I copied those conditions up there. Now let's ask nature to count the order characteristic. We noticed that nature knew how to solve this problem, how to find the current value in each wire. How is that possible? It's possible in view of the zeroth law of the theory of equations. This applies to any equation. It can be algebraic equation, differential equation, partial differential equation, integral equation, functional equation. It's all the same. So you count the number of unknowns and constraints in some manner. And if you want the existence of a solution, you want to please, I want one solution. It doesn't matter how rubbish it is, but I want one solution. Well, there had better be more unknowns than constraints. In other words, you try some unknowns and so it works. It should be easy to work a solution, make a solution work. On the other hand, if you want uniqueness, I don't care if the solution doesn't exist, but if it exists, it has better be unique. There should be very few solutions. Then there had better be few unknowns compared with the number of solutions. Yeah, so there should be enough constraints to cut down the number of solutions. But if you want both existence and uniqueness, they had better be equal. Yeah. And that's, of course, in linear algebra, for example, now rank nullity theorem, that kind of thing is a manifestation of this. So nature determines the values of a current instantly. So the number of unknowns must equal to the number of the total number of constraints. That's beta 0 minus 1 plus beta 0 minus 2. But if you rearrange the pieces, the order characteristic combinatorially is beta 0 minus beta 1 plus beta 2, and that comes out to be 2. That's the order characteristic of the sphere. Well, what about order characteristic of some more complicated surfaces, excuse me. So of genus G. So this is the way that people always draw a surface of genus G. So they're G handles, as they say. I don't like to say holes. And here you have those strange circuits. But let me give another digression. Every topologist throughout the centuries, throughout the 2 centuries or so, have been drawing a torus like this. Yes, you have seen this picture. So I used to be a card-carrying topologist. My card expired some time ago. And then I went to a conference, and one day I drew a torus like this. And then so this is my picture of a genus G surface. And there are G handles, and there are 2G new sort of circuits like this. And those are genuinely new in that if you impose the zero curl condition around this, they are not dependent on the old zero curl conditions around the faces. In other words, even if you impose that around each face, you don't have circulation, you cannot guarantee that you have no circulation around these. You might have some circulation. Of course, I'm reinventing the wheel of homology. Anyway, so here, beta 2, the number of constraints, must be amended to beta 2 plus 2g. 2g, that's the number of cycles that I introduced. So beta 1 equals, that's the number of unknowns, equals beta 0 minus 1 plus beta 2 plus 2g minus 1, that's the number of constraints. And if you rearrange the pieces, Euler characteristic comes out to be 2 minus 2g. And I'll give you the pleasure of working out a non-orientable case. At this point, I cannot help thinking that maybe I'm reinventing Hodge theory, because you see, Hodge theory says that in each homology class, or homology class if you like, you can find a harmonic representative. And this is all about harmonic functions. In other words, you want to minimize, in terms of some energy, the physical quantity, and that's, of course, going to give you the representative. But anyway, that's what it is. Okay. Now, it's time to conclude this lecture, really. And as in the Japanese theater, there is this great no, which is very serious, very tragic, and also very deep message and so on. And between two pieces of no, you have always a comical piece called kyogen, which kind of makes fun of what you have just said and prepares the ground for the next piece and so forth. So this is like a kyogen of the entire lecture. I started with a photograph of an apple tree, and these are apples. And somehow apples are very important in the history of physics. You know that Newton was sitting on an apple tree and something fell on his head, and he started thinking about gravity. I don't really defend that legend, but it's true that he had an apple tree in his orchard at home. So Newton said that, well, apple falls from a tree to the ground. Why? Because any two objects in the universe attract each other. That's gravitational attraction. And if you solve the differential equation, the trajectory of the apple, as it is pulled towards the Earth, and the Earth is, of course, being pulled towards the apple too, that looks like falling towards the ground. That's what Newton's picture was. Then came Einstein. He said, well, that's a very good approximation, but in fact, there's a much more beautiful picture. What you should do is to consider space-time and the metric, a Lorentzian metric of the space-time. And, you know, the presence of mass curves the metric, and if you sort of see the geodesic, so the straightforward motion of an apple inside that space-time, with respect to that geodesic, then it looks like falling towards the ground. But unbeknownst to most of us, there's a third Darwinian theory of gravity. Darwinian theory of gravity. I used to live in Cambridge, England, in the house that used to belong to Darwin's. So here's Darwinian theory of gravity. Darwinian theory of gravity says that a long, long time ago, in the history of evolution, there are two kinds of apples. One kind of apple, when detached from a tree, had the property of falling down. Another kind of apple had the property of falling up. And then natural selection took place, and the latter kind of apple, falling upward apple, suffered the reproductive disadvantage. Great pleasure and privilege to address this audience. And I'd like to end with a piece of numerology. Do you know how many seconds there are in a year? I learned this from my physics friends at Princeton, and it turns out that it's almost exactly pi times 10 to 7 seconds. You know this? The error is amazingly small. It's less than 0.4%. This is a leap year, I know, but even in a leap year, that's that. In case you're not impressed by this, replace pi by square root of 10. So now I'm talking about 1 year is approximately 10 to 7.5, and then the error is less than 0.25%. But pi is very useful because I use this for conversion in astronomical calculations, and pi is all over the place. Anyway, so it's about 3 times 10 to 7 seconds, whereas 1 century is 3 times 10 to 9 seconds. Of course, you multiply both sides by 100. Yeah, 3 billion seconds. Okay. By the way, if you are about to turn 93, shortly after your 93rd birthday, you pass through the 3 billionth second of your life. And when I noticed this, that is, shortly after your 31st birthday, you pass through 1 billionth second of your life. I was very excited, but I had just passed it, so now I have to wait until I'm 60. But by the way, I used to live, as I said, in a house belonging to Darwin, and we caught that anniversary for my wife. When she was turning 1 billionth second, I found out from her mother at what time of the night she was born. So we're standing on the balcony of the Darwin house with a champagne glass in each. 3, 2, 1, congratulations. Anyway, so let's go back. So now, I don't know who decided this, but in modern times, a lecture like this is supposed to last 15 minutes. This one lasted almost exactly, and that's 3 times 10 to 3 seconds, 30. So 3,000 seconds. So if you divide by one by the other, this is the last present that I would like to offer you today. It turns out, it so transpires that one lecture is a microcentury. So next time you go to a lecture, you are investing a microcentury of your life. And the next time you give a lecture, you are taking a microcentury away from your life. As I say, it has been a great pleasure and privilege. And I would like to thank you for your very kind company in the last microcentury.
Thank you, Tadashi, for this wonderful lecture. Are there questions for Tadashi?
Can you pick up? Oh, can you pick up the question? Because I don't look like it, but I'm half blind, so I cannot see anybody raising.
Camilo.
Yeah, Camilo, yes.
The one you suggested, what is the tree at the beginning of the right?
I'm so glad somebody asked that question. It's amazing how spontaneous people can be. Thank you very much, Professor Bellis. So this tree is a photograph which some of you might recognize. It's a tree that is standing by the great gate of the of Trinity College, Cambridge. That's the College of Newton. Now, I don't defend that legend about Newton, but it is true that Newton had an apple tree in Grantham in his manor, and this is a direct descendant from Newton's apple tree. And it is an old tree, no longer bears fruits actually, but it's standing there next to King Henry VIII statue and so forth, and that's a really famous thing. So that's one apple tree. Directly, I mean, provably, there's paper trail directly descended from Newton's apple tree. Next, if you went to Cambridge, England still, and it is better Cambridge, at the Center of Mathematical Studies, Mathematical Sciences, by the entrance, past the gatehouse, there is a small apple tree, maybe from this floor, maybe this tall, and it's a very young, so the baby apple tree, which bears tiny, cute fruits like this, and that's also descended directly from Newton's apple tree. And in fact, it was planted for the inauguration of that center. And I used to collect those apples because nobody was paying attention and give them to my friends. Grow your own Newton's apple tree. So that's the second Newton's apple tree in Cambridge. And third apple tree that is directly descended from Newton's apple tree is the Botanic Gardens of Cambridge University. It's a really beautiful place, and if you go there, right, not too far from the entrance, there's a really great and thriving apple tree, really in the prime of its life, and which bears wonderful fruits. And so there's even a bronze plaque that says Newton's apple tree. So that's a third apple tree directly descended from Newton. They all have provable paper trail. Well, somebody looked at them. They all belong to different species.
Stan.
So
Yes.
you gave beautiful examples of how physics can be useful in mathematics. But all they are classic physics. So I understand that the quantum physics is not useful in mathematics.
Excellent. So I'm very glad again that somebody, it's so as if I'm planting questions. So the question was, yes, all those are classical examples that overeducated people have learned in school and so on. I'm rediscovering or I'm rederiving the same results. What about new things? What about the more recent things and so on? There are some recent examples, but I think I can offer no better defense than to say that the history of the last 40 or so years of high energy physics really transforming the landscape of geometry and topology and elsewhere. Yeah? Much of it under the leadership of people at this place is really the most powerful witness to that phenomenon. And people have understood one thing after another, and mathematicians have to run behind. Sometimes there's much advantage to running behind than in front. So I think there are many, many examples which I didn't offer because this is the beginning. I'd rather you, people who are cleverer and more imagination than I, went on to discover this.
Any other questions? Okay, let's thank Tadashi again.